The last topic in section 3.4 is piecewise defined functions. These are functions defined in pieces. So here's an example. What this notation tells us is that f of x is equal to x squared when x is less than 0. It's equal to 2 when x is 0, and it's equal to x plus 2 if x is greater than 0. So we're to find these three values. Find f of negative 2. So we go, when x is negative 2, which one of these do we use? The first one, right? Because that would be less than 0. So we plug it into the first one, and we get 4. So f of negative 2 is 4. Find f of 0. When x is 0, well, they told us f of x is 2. And f of 3. Okay, so x is greater than 0, 3 is greater than 0, so we use this one, and we get 5. Okay, now we want to determine the domain of f. I think the easiest way to do that is just to come up here and look at what values of x we're using. We're using x less than 0, equal to 0, and greater than 0. So that covers all real numbers, doesn't it? There's nothing left out. All real numbers. Now let's graph this. Okay, to graph it, I have to graph each portion. So when x is less than 0, I can choose numbers less than 0, but if I choose those, I have to square them. So if I choose less than 0, what, negative 1, I would square that and get 1. I can choose negative 2 and square that and get 4, right? If I'm choosing negatives, this is what I have to do. Okay, this one is just a point, right? X is 0, y is 2, x is 0, y is 2. So I know this point right here is on my graph. And now, what do I do when I have x's that are greater than 0? Well, if I choose x's that are greater than 0, such as 1, then I add 2 to them. 1 plus 2 is 3, 2 plus 2 is 4, okay, and I get 3 plus 2 is 5. Okay, we had that one here. Let's see what this graph looks like. So we know it includes this point. We know it includes negative 1, 1, negative 2, 4, but it's every point between there too, right? Because we just say less than 0. So less than 0 would be immediately after 0. You don't have to go all the way to negative 1 to be less than 0. So we know that we can't plug in 0 here, so I'm going to put a hole. But what happens after that is, this is that quadratic, right? So I could even put in, let's put in, since I can graph this, negative 3 and get 9, negative 3 and get 9. And so now I can see where we have a half of a parabola here, right? And it comes all the way down, gets as close to 0 as possible, but never at 0. That's why I put that hole there. Okay, then at 0, x is 2. Then as we step off from 0 and go up, we have 1, 3, x is 1, y is 3, x is 2, y is 4, x is 3, y is 5. So coming off of here, we have this line. And it is a line, right? And it gets awfully close to 0, but it can never be 0. But notice what happens here. So we come down on this parabola leg, we get almost to 0, and now here we are. We pick up right there when x is 0, y is 2, and then from there on we go off on this line. Okay, so now we can look at this and determine the range, right? What's the lowest value of y on this graph? Well, it gets close to 0, but it never really gets there, right? So it goes, we'll use an open interval to show that we get close to 0, but we never get there for y, comma, and then look, it's pointing straight up to positive infinity. The last question is f continuous on its domain? All that means, let me make it out, it's continuous if it has no holes, or breaks in the domain, in the so in other words, it's continuous because we don't ever run out of x values. We don't have a break in our x values. Once you start the domain starting at negative infinity, there's no break to positive infinity. We have this little jump right here, but it's filled in. We don't have a place where there's a hole in our domain. It goes from negative infinity to positive infinity. We don't have, recall in the past, we've seen things where we want to make a hole and we have to union this interval and that interval, but our domain, once we start it at negative infinity, it just continues. So yes, it is continuous because it has no holes in the domain, right? Okay.